You should control my Zoom. I apologize. I am now.
It's okay. I'm
Thank you
just
so
making sure.
thank you so much. All
You're
right.
welcome.
So for the people watching this later, because I just started recording, um, again for A, we just want to lay out the dependent and independent variables. So I want to define what my independent is, and based on the prompt, I want it measured. I want it the population relative to time in years. So time in years is my independent because I want population based on that variable. So my independent is time in years, and I called it T. You can call it X. And then my dependent is the quantity that is relative to the independent. So I want to model the population of China at T years. Okay. And then we just laid it out. So the independent goes in the horizontal, the dependent goes on the vertical. We labeled everything, and we just put a little nice, I think the population is going up, so we put a little nice swoop, right? Right. And then C, the one we were getting to, it says discuss the validity, and so it's a fake graph, so that would it's not a valid graph, but the graph could be more accurate if I knew more Chinese history. Just like, so on the test, I'm not going to give you one on Chinese history. It'll be something else. And so basically, you'll just be discussing the validity of your graph. Uh, I forget, like the one example I did last semester, you had a graph, and it was about like a dog's height over T years. So as the dog ages, his height goes up, right? And so in this particular example, the graph was a line with an increasing slope. And so as far as that function goes, it's not a very valid model, right? Because if you have a line with increasing slope or positive slope, so the line's increasing, the dog is going to get bigger for forever. It's never going to end. And so your model should kind of match what reality predicts or reality is. So anyway, that's it. I'm really more interested in A and B for this, but C, you can be creative. Right. So that's it. There's no real computations for number one. It's just a matter of laying out what I asked for. So two. You have $500 in your bank account. Every month you make $600 and deposit it into your bank account. So it says give a linear function or linear equation f modeling the amount of money in your bank account where, and again, so I'm kind of setting it up for you. I'm telling you to have a function f and then let x be the number of months, right? How much money will you have in 3 months? How many months will you, until you make 3,500? And then sketch. Right, let's do it. So two, there we go. 2a. So I want to create this function f. And so for this sort of problem, I'm essentially giving you the function, but I'm giving you it in words. So you have $500, right? So that's your initial. You initially have $500 in your account. Every month you make 600 and you put that in your account. And for some reason, we're assuming that we're not taking money out. So maybe, I don't know, maybe you're making a lot of money and this 600 is just like extra savings, right? So if I start with 500, right, write that. So f of x equals 500. So that's what I start with. So that's my initial value. And then every month, I'm adding 600. So every month I add, so I put plus. Again, we're just translating it into an equation. And then I add 600 every month. So the way you write that is 600 times the number of months that have progressed. So 600 times x. Right? So every month I add 600. Right? And there you go. So you don't need to really, you don't need to do any like math, algebra, I should say, to find this equation. You're just rewriting the prompt. You're just taking the information you're given and rewriting it as an equation. Okay. Questions there? So that's A. And again, x is the number of months. And that was given to you in the prompt as well. I kind of told you what the variables were. All right, B, how much money will you make in 3 months? So if X is the number of months that have progressed, and F is the amount in your bank account, maybe I should label that amount in account at X months. Kind of squeezed in there. All right. Then if I want the amount of money in 3 months, what am I going to do?
Did you put the 3 where the X is?
Exactly. Yep. So you just do F of 3. So you let X equals 3. And then you get some number, right? So you get 500 plus, and so X is 3. So I plug in 3 where I see the X, 600 times 3. And there you go. So that's 1,800 plus 500. What is that, 2,300? Right, so in 3 months, I'll have 2,300 bucks. And you could have also, for that kind of thing, you could have also just thought of intuitively, right? If I start with 500 and every month I add 6, I start with 5, 600 is 1,100, 600 is 1,700, 600 is 2,300, and that's 3 months. So you can kind of do it iteratively, where you make a little table essentially implicitly, and that helps you. That will help you find it too. So that's B. C. How many months will it take you to have $3,500? And so, like I was just saying, actually, you could make a table for these two problems, right? You could make a little table. So the one way you could do it, you would do you do X, F of X, right? And so 1, 2, 3, I can't count. 1, 2, 3, 4, 5, maybe we'll do up to 5, all right? And so you could do a table. And so I start at 500 bucks. So at 0 months, I have 500. And then every month you add 11, or every month you add 600. So the next month I have 1,100. And I add another 600, 1,700. Another 600, 2,300. Another 600, 2,900. And then another 600, and I get what, 3,500. And you could keep going. But you'll note that the question itself is asking, when will you have 3,500? And so when you look at your table, you'll see it's at 5 months. Right? So that's one way you can do it. However, I should note that if the value that I give you, so if I gave you like 3,600, you wouldn't really be able to make a table. Well, you could kind of get an estimate, right? You would know that it's just slightly more than 5 months would give you 3,600. So this really works well when it's kind of exact answer, like you'll have a nice integer answer. This works really well. But if you have some weird decimal things in your answer, like if it was 5.121 months, it wouldn't work so hot. So this is way 1. But the second way, so this is number 1. The second way you can also do it algebraically. So number 2. So the way you would do that is you would take your function f, and you want to solve for x when it equals 3,500. I know what f is, right? We defined it in part A. So I can plug in the definition of f here. So I get 500 plus 600x equals 3,500. And now we just solve for x. So both will give you the same answer, of course, but if I do it this way, I want to get the x by itself, right? So I bring this 500 to the right-hand side by subtracting 500 from both sides. And so I get 600x equals 3,000, because 3,500 minus 500 is 3,000. And then I just divide by the 600. So I just get x. I'm kind of out of space, but I'll put it down here. X equals 3,000 over 600, which is 5. And that's the same as what we got up there. All right. So either do it algebraically, which is really the preferred method, or you make a table. And either way will get you an answer. The table might not work if it's a decimal answer, but if it's an integer, you'll be good to go. So questions? Okay, is that it? Oh, and we got a sketch. Sketch isn't bad. I think the algebra on that last part's the hardest part. So to sketch it, it's a line. So sketching lines is usually not too bad. So remember if my function is f of x, 500 plus 600 x. So what you'll do is, where should I put this? There you go. What you'll do is you'll make a, well, x and y, right? And so this is x. And again, that's in months. And then you put the f on the vertical. And so that's in dollars. And so when x is 0, I have 500, right? Because that's my initial bank account amount. And so when we did lines initially, I had said that you just need to plot 2 points and connect the dots to draw a line. So if I do 0 and 1, at 1 we said it was 1100. So I guess it should be higher. I'm sorry. There you go. We'll put that here. 1100. Then I'll put a dot at 1100, dot at 500, and I'll connect the dots. So let me see my staplers. Let's see if this works. There we go. And you're good to go. And so this is my function. Oh, I'm sorry. This is just, yeah, that's fine. All right. Right, so any questions? You can also call this y on the vertical. So if I do y equals f of x, your y is in dollars, but I don't know. It doesn't really matter. And that's your sketch. Again, so on the test, if you just I'm just looking for a sketch. So when I say sketch, I mean like I want to see that it's going the right way. I want to see you've labeled your axes. I want to say you have at least a couple points on there that you plotted. But I'm not going to take off points if like it's not like in a nice grid. It doesn't have to be perfect, is what I'm trying to say. As long as it has the basic fundamental features, like that the line's going up, everything's labeled, it'd be good enough. All right. So that was 2. Oh, well, this is the dog one. Oh, but it has a weight, not a height. It's the same thing. So let me show. So 3. And so yeah, so the first grouping of these, the first 3 are all like, well, the first problem is just functions in general. The next 2 are line problems. And then 4 will be an exponential function. So that kind of covers that first unit we talked about. So a dog weighs 5 pounds at birth, and a year later weighs 40 pounds. Give a linear equation modeling the weight of the dog after X years. How much will he weigh in 3 years? Give a sketch of F. Discuss the validity. All right, so this one's going to allow us to discuss the validity a little easier than that first problem did, or a little more like concretely. But let's start with A. So let's see, so A. So give a function F. So we have to use, we're not given the function here, right? So in 2, I had said that it was kind of given in the word problem, and you just had to translate the words into the math equation, f of x. So for 3, we can't really do that because we're not given enough information. We're only given that he started at 5 pounds and a year later weighs 40 pounds. So we have to use a slope formula. So it's a little more algebraic, right? So we have to use the formula, use y equals mx plus b. Right, so b is your starting value, or your initial value. So that will be his initial weight at birth. Weight at birth. And then the m will be the slope. And so the slope in this problem is going to be the amount of, what is it in pounds? Yeah, will be the amount of pounds he gains per year. Pounds gained per year, right? And so we know what his initial value is, right? We know that the problem says he started at 5 pounds. So right off the bat, we have mx plus 5. So the only thing we have to do is figure out what m is. And for that, we have the slope formula, remember. So for m, for slope, we have m equals, it was change in y over change in x, or rise over run. So it's y2 minus y1 over x2 minus x1. All right, so and you can plot this first. So I made the sketching of it part C. So, but if you want, I don't know, I always find that when I'm finding slopes with rise over run, I always like to plot the points on a grid or on at least a sketch of a plane. So if you want, you can kind of do part one A and part C kind of together, but it doesn't matter. In any case, the top will be the change in the weights. So he's 40 pounds in year 1. So it's going to be 40 minus, he's initially 5, and then over the amount of years. So it took 1 year to gain 35 pounds. All right, does that make sense? So again, the slope is just pounds gained per year. So what we did to find the slope is we took how many pounds he was in 1 year and how many pounds he was in 0 years and took the difference. So this is the amount of pounds he gained in the first year over the first year. So you're just finding like the average, how many pounds he's gaining per year. In any case, this is just 35, right? 35 pounds per year. Awesome, but we have all the components now. So y equals 35x plus 5. And that's part A. So again, you're just using the slope formula to find the equation of the line here. Right. B, how much will he weigh in 3 years? Right. So if this is our equation, y equals 35x plus 5, and x is, I didn't label it, I should have labeled it. X is number of years, and y will be the weight. Right? And in the problem I said this was f of x. So you can also write y equals f of x equals mx plus b. So maybe I'll put that down here. Right, so f of x equals y equals that. Right. But anyway, so if x is 35, or x is the number of years, and we want his weight in 3 years, we just plug in x equals 3, like we did in the second problem. Right? It just happens to be the same value, but it's the same process. So that x equals 3 again. Get, so f of x, or f of 3. And then you plug in x equals 3 back into the equation we found. So it's going to be 35 times 3 plus 5. And that you can plug in your calculator. I don't know what that is off the top of my head. I'm sure it's not too bad. But so 35 times 3 plus 5. 110. 110 pounds. So he's a big boy. All right. Questions with that? A or B? All right. And then C, give a sketch. So as I said, you could have done this initially if you'd like to sketch or plot the points before you find the slope, but it's all good. So let's see. So on the horizontal, we have the independent variable. So that's going to be the years because we're allowed to change that. We just kind of plug in whatever you want. So this is X, and that's in years. That's how old the dog is. And then on the vertical, I have his weight, and that's in pounds. And you can also put like Y there, or F of X. It's kind of the same thing. And then we plot some points. So he starts at 0 years, remember? At 0 years, he was 5 pounds. So I'll put a dot at 5. And then at 1 year, he was, what was it? 40 pounds. So I don't know. My scales are never right. So I'll go up there. And then at 3 years, he was 110, and that's probably off my scale. So I apologize. As I said, my scales are horrible. But now you connect the dots. And so that's f of x. And again, as I said, I want to stress, I'm not gonna take off points if your plot like mine is not to scale or it's not perfectly laid out. All I really want you, I really am looking for is everything's there though, fundamentally. Like if the line has a positive slope, I want to see that your line's going up. If the line I want to see things labeled like pounds and years in this case, variables, just that kind of thing. I don't care if it's like exactly proportional. Right. There we go. Again, 2 dots and connect the dots, and you're good to go for a line. And then D, discuss the validity. All right, so this one there is a significant problem with. If this is the graph of your dog's weight, what problems arise with this graph?
He's going to be huge.
Right? He's gonna be massive. He's like Clifford. He's literally Clifford, the big red dog. If you're not familiar, hopefully you know Clifford. Yeah, there's no stopping his growth. Every single year, he gains 35 pounds consistently. That doesn't happen. Like even the biggest dogs, I think, stop growing by 2 years. So, like in reality, so I'll just write dogs will stop growing. So it's not a good model at all. In reality, what you would probably see, and I don't really know that much about dog growth, so note, it probably really looked like this to some extent. It would go up, right, for the first year or two, depending on the dog. I put 1, 0, and it won't start at 0 either. I guess I should make this higher, like that maybe, right? And then what will happen? It will just plateau. Maybe if he gets really fat in old age, that might happen. But yeah, it will just plateau and flatten out. You wouldn't expect it to keep going, right? But yeah, so this would be really what your graph would look like if you modeled your dog's weight, like if you took actual records, not a straight line going up, just because it's not realistic. All right, so that's 3. Let me move this. I like to waste paper. All right, 4. A petri dish has 100 bacteria in it when you start an experiment. So again, kind of keep track of things. We have 100 initially. You determine that the bacteria are growing at a rate of 3% per minute. Right, so those are the things you need to take away from this problem. You start with 100, they're growing at 3% per minute. That's all you really need to know. Give an equation, an exponential equation, modeling the bacteria's population. And even here, if I hadn't even said exponential, if I just said give an equation, Q of t, then you still would have expected it to be exponential, right? Because it's growing at a rate of 3% per minute. So whenever the growing or the growth rate is a proportion or a percentage of the population, it's exponential by definition. So I'm giving you, it's kind of duplicate information here. You should already know it's exponential based on the fact that it's growing at a percent. If I said it was growing at 100 bacteria per minute, then it would be linear, right? Because it's growing by a fixed absolute value each time. So remember we talked about the difference between linear and exponential growth is that linear grows by the same or goes down by the same each time. And in contrast, exponential growth or decay either goes up or down by the same percentage each time. So here it's going up by this 3%, it's exponential growth. All right, so let's write it. And the only thing you really need for part A is to remember the formula. So Q of t, this is the one you'll need. So Q of t equals Q naught 1 plus R to the t, where R is the growth or decay rate as a decimal, and Q naught's the initial population. And by initial population, it could also be like the initial amount of carbon-14 you have. So it's just the initial value of whatever you're modeling. So initial, but in our case, it is a population. So questions about this? So remember this formula is you'll need for this problem. Right. And T here will be in minutes, but T can be really whatever. T here is in minutes because if I go back to the problem, it's 3% per minute. So if we use our R value as 3%, then the t will necessarily be in minutes because it kind of inherits the units from the r value. Okay, so let's just plug everything in. So my q of t equals 100, because that's my initial population of bacteria, 1 plus 0.03 to the t. And that's it. So assuming you know the formula, this first part is just a matter of plugging in things appropriately. And remember, 3.03 is just 3%, because that's the same as 3 over 100. Right? And you always want to use the decimal, because most calculators don't understand percents. All right, so that's A. Letter B, how many bacteria will there be in 30 minutes? So how do I find how many bacteria there will be in 30 minutes?
Plug 30 in the T.
Yep, so again, you can kind of, it's the same kind of question that we did for those past two linear ones. The only difference is our model is a different type. So it's Q, so I mean, I'll say it again, let T equals 30. And you get Q of 30 equals 100. And just be careful when you plug this in your calculator, 0.03 to the 30. All right. If you have a scientific, it's much easier, I think, usually, just because you have better, it looks better, but it will work with any calculator. So let me put it here. All right, so 100 times 1 plus 0.03, and then all to the 30. All right, it's, geez. Oh, that's my mistake. I'm sorry. I put a times, not a plus. Like, that doesn't look right. There you go. That looks better. So 1 plus 0.03, not times 0.03. And it looks like you get about 242 bacteria, 243. So I'll round up to 243. Cool. So the growth rate's not that big, right? It's only 3%. So even after 30 minutes, we only have 143 more bacteria. But if you keep going, it will explode rapidly because it's exponential growth. The only other thing I wanted to note is up here, before we do the graph, up here, and the problem for R, it said that it was growing, right? If it was decaying, my R would be negative. So I guess I don't know where to put it. I'll put it on here. So if decay make R negative. So for instance, if it said it was decaying at a rate of 5%, then my formula would be 100, 1 minus 0.05 to the t. All right. So just kind of remember that. You have to read it from the problem and kind of get which one you should be using. So I'll write that down here. So note, if decaying at a rate of R%, use Q of T equals Q naught 1 minus R to the T. Right. Everything else is about the same though. So any questions? And then C, sketch Q. And again, it's a sketch. I don't want, don't kill yourself making it super precise and pretty. I do like if it looks pretty, but don't worry if it's not the prettiest graph on the planet. So this is growth. See, I can't even draw a straight line. So I put my independent variables T, and that is in minutes. My dependent is my population, and I guess bacteria. Doesn't really matter. Be as precise as you like. And then my starting value is 100. So at 0, I'm 100. And for exponential decay or growth, you just kind of put in what it should look like. So for instance, it starts at 100, and it's just going to kind of go like that. All right. If you want, you can put in 30 here, and maybe that will be 243. So you can put in that point if you want, but just know it's, this will be what exponential growth looks like. It's just kind of like a swoop up. Decay would be a swoop down. So let me, so again, so note for decay, your shape is going to look like this. Okay. So it kind of looks like a down. The important thing here is that it never crosses the axis, the horizontal axis. It will never go down into like negative land. You can see that algebraically too, just because raising a positive to a power will never make it negative. So it's always above the x, or in this case t-axis, but it will just be kind of decaying like that. Right? And it'll get really close, but it'll just never touch it. Okay. So those are the two cases for exponential growth and decay. Just kind of know the graph shape, know the formula, know how to plug in values and find what the value would be at whatever time. So know how to use your calculator in that regard. But right, and then just the last three are all about geometry. Let's say geography. We don't do that. I don't even know what that would be. All right, so 5. Yep. So, all right, so this one's a little silly. I don't know, but it's good. So suppose you have 100 meters squared field divided up into 10 smaller fields, all of even area. What is the area of each smaller field? If the height of each smaller field is 2 meters, what is the width? And then C, what's the total area of 5 of the smaller fields? So it's just kind of a weird question about areas, but I don't know. There's not much you can do with areas. So for A, so you can draw a picture. So it's 100 meters squared field divided up into 10 smaller fields, all even areas. So for A, what is the area of each of the smaller fields? The entire field is 100 meters squared, right? Entire field. So if I have 10 smaller fields and they all have the same area, then the area of each must just be 10 meters squared divided by 10. It's a number of same size smaller fields. Right? And so you just get 10 meters squared. Makes sense, right? You're just taking the whole area of this big field, and maybe you want to plant like potatoes on one small field and like corn on the other, and you're breaking it up into smaller chunks. B, now B asks if the height of each smaller field, and these are all rectangular, so if the height of each smaller field is 2 meters, what is the width? So basically, I know that I have some rectangular, I guess it didn't have to be a rectangle. I feel like all fields are rectangular though, so it's not true. I have some smaller rectangular field, and I know the area is 10 meters squared. So if I tell you that the height is 2 meters, then what must the width be?
Five.
Yeah, right? Because to find the area of a rectangle, you do length times width. So if this is 2 and their product is 10, then that must be 5. What was this? What I call this? The width? Yeah. So 10 meters squared equals length times width, and that's 2 times W. So that tells you equals 5 meters. Right? So you get 5. And then C, what is the total area of 5 of the smaller fields? So if each small field is 10 meters squared, what's the area of 5 of them? So what's the total area? Right, so like you can draw a picture, I guess. So you have a boop, boop. Maybe they're, I don't know, pretend they're touching. Boop, boop, and maybe there's another one. Boop, 10 meters squared, 10 meters squared, 10 meters squared, 10 meters squared, and 10 meters squared. So what's the total area of these 5 fields?
50.
Thank you. 50 meters squared. You can either add them up or you just multiply 10 times 5. Cool. So that was 5. I don't remember what I put in the test. It might have, I think it was involved chocolate, but I'll have to check. It's similar-ish. All right. 6. There we go. So David leaves his house to go to school. He walks 200 meters west and 125 meters north along the sides of a rectangular field. How far did he walk? What is the perimeter of the field? What's the area of the field? And how far would he have walked if he walked diagonally across the field? Let's see. So let's set it up first, right? So let me draw David. So he goes west. I'm going to put him over here. Right? He's going west. Oh, west and then north. So I'll put him down here. So there's David. He walks west. So I'll say that's left. So it's west, 200 meters. And then north, 125 meters. Right? So that's where he goes, right there. And this is his house. This is his school. Great. So, well, the first part, A, how far did he walk?
$325.
Exactly, right? You just add them together. So 125 plus 200 equals 325 meters. That's it. All right. C, B. What's the perimeter of the field? So remember, this is the field in the middle. Right? And I don't know, maybe it's got grass in it. And a flower. Right? So if he walked 325 meters to get to the school, what is the total perimeter of the field going to be? Right, so it's 200 meters here.
650.
Yeah, exactly, right? Because it's the same on the top as it is in the bottom, and it's the same on this east side as it is on the west side, because it's a rectangle. So all you do is add up all the things. So you can either do 125 plus 200 plus 125 plus 200 and get 650 meters. Right? You can do it that way, or you can just realize that he walked half the perimeter. So you just double what you put for part A. Either one. C. What's the area of the field? So it's kind of, we just did this in the other one, right? Length times width. So it's a rectangle. So the length is, I don't know. I don't know. You never know. I don't think there's really a canonical way to say length or width. I'll say this is the width. So it's 200, and then it goes to 125 up. So it's going to be 200 times 125. 200 meters times 125 meters. And that's the number. It's a big number. Let's see. So it's 200 times 125, 25,000. It's decently large. So it's 25,000 meters squared, right? And so for these area and perimeter stuff, I'm going to be looking for the units. So make sure your units are correct, right? Because that's part of what we learned for these. Well, we're doing more units in the next unit, but you know, it's important that you know how the units work for areas and perimeters and volumes. So when I'm multiplying 200 meters and 125 meters to find the area, I'm also multiplying the units together. So meters times meters results in meters squared. Right? So make sure you put the units on. And then D, so how far would he have walked if he walked diagonally? You ever see that in Harry Potter? I don't know, I guess it's not a GIF. It's like a meme. It's like diagonally, and he's trying to go to Diagon Alley. It's great. I love Harry Potter. So by diagonally, I just mean he's, instead of going over and up, he's going to just cut across. He's going to take the path, the shortest path. Like that. Right. So any ideas how we can find that distance across the field? So you have to remember that some of our triangle stuff, right? So when you go diagonally across a rectangle, you naturally get two right triangles. So if I look at this bottom right triangle, I'll pull it out and redraw it. So basically this is what I got, right? It's a right triangle because it's half of a rectangle. So we'll cut across the lengthwise there, or diagonally. So you get 200 meters, 125 meters. And so what technique or what theorem do we know to find the hypotenuse? For a right triangle. Maybe I'll call this A and call this B, right? And call this C. So if you recall your notes, we talked about the Pythagorean theorem, right? So use Pythagorean theorem. So that says that A squared plus B squared equals C squared, where C is the hypotenuse. So the only thing that's really important with the Pythagorean theorem is that you know that C is the hypotenuse. It's the biggest, longest side on the triangle across from the 90 degrees. So that's the hypotenuse there. So we're missing the hypotenuse. So what I can do is I can plug in the two smaller legs or two smaller sides that we know, which is 200 and 125. So I'll do another sheet of paper. So I get, what do I get? There we go. So I get 200 was, oh no, 125 was A. It doesn't really matter, but plus 200 for B. And you're squaring them both. And this is equal to C squared. All right. And now it's just a matter of solving. So you use your calculator. So I'll first add these two together. So I get 125 squared plus 200 squared. And make sure you're actually squaring them. Don't just double them. So I know sometimes it can be tempting to be like, oh, it's 125 times 2, but it's not, right? It's 125 times 125. So that's what the squared means in the exponential, like up there in the exponential. Anyway, we get that ugly number. So it's 55,625 equals C squared. And then, like we said, to find a number, and again, this is squared, right? So you can't just divide by 2. So you have to take a square root. So the opposite of a square in the exponent, or 2 in the exponent, is a square root. So what that's saying is that when I take a square root, it's saying what number, when multiplied by itself, will give me this number. So in this case, I'll take a square root of both sides. As I said, the square root and the square are opposite. They're inverses, so they undo each other. And so I end up with just C. So C itself is equal to the square root of that ugly number. And so that's, you need a calculator. So in my calculator, the button is this blue square root above the x squared. So I'll do second, which activates the blue button's square root. And then I'll plug in my number, 55625. And I get that uglier number, and I'll round it up. So 22,000, or wow, 236. Okay. And that is in meters. And I guess I should probably put an approximation sign. It's fine. I've been rounding. Any issues with the square roots or the squaring or using your calculator to find square roots or anything like that? All right. And so that's 6, and we have one more. Cool. We're perfect on time. So 7. There we go. 7. Oh, this is what I mentioned in class, right? With volumes. So you have 2 tree trunks on your property. One has a radius of 0.75 feet and is 10 feet tall. The other has a radius of 1.25 feet and is 7 feet tall. Which tree trunk will give you more firewood? Right? So basically, we just want to find the volume of both and see which has a bigger volume. And so they're both cylinders, right? They both have a circular base and they're just trees, a tree trunk. So, and I'm assuming they're perfect cylinders. Don't worry about like knots. Maybe there's a branch, just ignore the branch sticking out. Maybe you've trimmed it. Maybe you put it through one of those machines that makes telephone poles. I don't know. You've done something to it to make it perfectly cylindrical. And we're going to find the volume of both. So I'll make two kind of competing charts. I'll do this one as tree 1, and this one is tree number 2. So for both, I just want to find the volume. The bigger volume is the winner. So for the first tree, I have a radius, so I'll say of 0.75 feet and a height of 10 feet. For the second tree, I have a radius of 1.25 feet and a height of 7. All right. And so now we just need to know the volume formula for a cylinder. So recall, and I'm not going to ask you for the volume of like a pyramid or the volume of a, I don't remember what else we did. A sphere. I'm not going to ask you for that kind of thing. Just know the volume of a cylinder, know the volume of a cube and a rectangular prism, length times width times height, and a cube is side times side times side. So know those two, and then the cylinder, and that's all you'll need. But if you recall, this cylinder is the area of the circle with radius r, just times the height of the tree. Right? And again, you can remember this formula because it's the area of the base times the height. So you're basically just taking the area of that bottom cross section and multiplying it by how high you are. And that's kind of cool actually. But and we plug it in. So for this one, I get, so V equals pi times r is 0.75 squared times 10. And this one is pi 1.25 squared times 7. Right, and now we need a calculator because we can't do anything with pi without a calculator really. So let's see. So, oh, and you know what we can do? We can even leave the pi alone first. So let's focus on this 0.75 business. Oops, sorry. So 0.75 squared. I put parentheses around the 0.75. I don't think you technically have to. I just like putting parentheses around things. And then times 10. And so that gives me 5.625. And now we'll throw the pi in. So times, so my pi button is in the blue here. So I do second pi. And then I get that thing. What is that? About, I'll say 17.7 feet cubed. So do know, so remember too, if you don't have a pi button on your calculator, you can just use 3.14 and that'll be fine. And this one, these are kind of, I don't know, tiny trees. I imagine they'd be bigger, but they're not that big. So again, I'll do 1.25 squared times 7. And then I'll throw my pi in there. So I get, this one's so much bigger. So this one is about 34.4 feet cubed. Right. So it's crazy, isn't it? It's kind of remarkable. So basically the tree that has this, the difference in the radius, the radii aren't that much, right? It's like what, half a foot. But, and this one's 3 feet taller, and it's still half the volume. It's pretty remarkable. So this is more firewood. So tree 2 gives more firewood. Just because of more volume, but that's the thing. So it's really interesting that the radius is what's really important. The height doesn't really matter so much. What's going to give you the volume is the radius. The more radius you have, the more volume you're going to have, and it's going to grow exponentially actually due to this squared business and the radius. So we'd have to, for this tree to have more volume, we'd have to really increase the height quite a bit. We'd have to double the height actually. If we put 20 here, we'd have just about the same. That's kind of cool. We'd have just about the same if you put 20. So this tree having only ½ a foot less radius would have to be twice as tall for it to be the same as this volume for that tree, which is 3 feet shorter and yet ½ a foot more radius. So any questions so far? Anything at all? That's the end of the test. So be prepared, as I said, know some of the volume formulas, rectangular prisms, cube, and then the cylinder one. Know the equations for the linear and exponential models. Know the equation for the slope. I think that's it, as far as like knowing formulas goes. And yeah, any questions, issues, problems? All right, so I'll see you Tuesday. If not, I'll see you then. And feel free to email me or email me tomorrow if you have any questions, or Monday if you have questions, and we can go over things as well. So, well, good luck. Have a nice weekend too. Yeah.
Can you say that what we need to know, like the formulas again?
Oh,
just wanna write
sure.
it down.
Sure. So, know y equals mx plus b. Know the slope. So y2 minus y1 over x2 minus x1. So this is line stuff. Know the exponential stuff. So q of t, q naught 1 plus r to the t. So this is growth, exponential. And then know the other one for decay, I guess. Decay, exponential. So those are both the exponential formulas. And then what else? Oh, the volume stuff. The area of rectangle. I think that's all we used, right, for that. So that's a length times width. And we used the Pythagorean theorem. I forgot about that. Pythagorean theorem. I'm never good at making concrete lists like that. So a squared plus b squared equals c squared. So again, that's the hypotenuse. Maybe I should spell it out. Hypotenuse.
Are you gonna post this?
The video?
Yeah.
Yeah.
Like how you usually post all the notes?
Yeah.
Okay.
Yeah.
Awesome.
Yeah.
Thanks.
Yeah, no problem.
Just so I can have something like if I get lost, because I'll go over it again.
Yeah,
and
totally.
Make sure I know.
Yep. So it's a side cubed. What else? Oh, rectangular prism. So a rectangular prism, as I said, it's really just a box. So that's just length times width times height. And then is it your volume? I should put volume here. And then, the one we just did, the cylinder. So this cylinder. So my volume is just pi r squared h, right? And so I didn't like label all these really. H is the height, r is the radius, length, width, height, and then side. Right? I think that's about it. That's all we used. So I mean, that's all. It's like a whole page. But yeah, that should be good. All right. Any questions? Anything
Okay,
else? Yeah.
Okay, can you see me? Like, can you see my
yeah.
screen now?
Yeah.
All right, so I have this app that I downloaded last semester for a math class, but it has like everything on it, like a graphing calculator.
Yeah.
It's really nice. Would that be okay if I use that?
Yeah, you can use that.
Okay.
Yeah. Yeah, it's the best we can do. Just it'll be like the honor system, not to cheat. It's like, what up, coronavirus. Anything else? Was that a yes? All right. So I don't know if Cotton said anything, but I think we're good then. So I'll see everyone on Tuesday. Feel free to shoot me an email if you have any questions.